Good morning, everybody. This is Hasan Aktarakçi from our Madrid office. Uh, this month, we're launching like 4 different webinars starting this week. And every week, I will give one short webinar about EarthImager 1D, and next week will be 2D, and following will be 3D. So we walk through all these software. I will show you the features of our softwares and also how you read your data, enter your data, and choose your presettings and make inversion, and how to change color scales to which helps your interpretations. But today we will start with EarthImager 1D, which is uh, uh, forward one inversion software of vertical sounding mainly. Here you can see on the main page, and I'll give you here is the link, which is if you have a software, our software, you can go also our web page. You can download for the latest version of that software, which is free of charge. And if you don't have any software, you can also download from through this link. There's a demo version of our software which can install in your computer and use it in during the 1 month. At the end of this seminar, with short seminar, you can just type your question or raise your hand, ask me anything about this, what we go through today. I will try to explain and answer your questions. Okay, let's start with this. With our again, here is the link. You can download it. Okay, typically is a vertical electric sounding data. What you have is here apparent resistivities on meters, and here's this is a typical Schellenberger vertical electric sounding. Half of electrospacing of Schellenberger, current electrospacing, which is typically how we try to do with plotting our data. If you have a Werner, you have Werner over here. If they have typically vertical sounding, you use Werner and Schellenberger, but you also can use other array types. I will show you later on with our software on that you can do that as well. Here's a typically vertical sounding is from starting is small AB, half of AB spacing, and then you just plot in the apparent resistivity. If you're on the field, I will always recommend to use this log-log plot, which is this is a log-log paper. Just put a transparent paper top of it on the field. For each measurement, just drop on your values on the log-log graph, then you can follow up your measurement like this. So you expect generally for smooth measurements. If you anything like this here doing the measurement like this point, for example, or this point like this, that means these are like a noisy data. So there can be many different reasons. Maybe it's like a long geometry, or you have really noise in that point. So you can just go and repeat until you get like a very nice point. So that's what's important to in the field. Just go with like a transparent log-log paper. Just draw all your measurement during your measurement on this paper. Make sure that all your data got a good quality. I mean, they get a good smoothing. On the right side here, you will see that I'll show that also in software, that the model, which is the geoelectrical model. So what you're trying to do is, this is your field data on the left side. Try to convert this field data to geoelectrical model like this, which has a resistivity values, and then these are the depth values here. So depth and resistivity values. So that's all we try to do to obtain information from one dielectric sounding. Depth values and resistivity values, which is we assume all these layers over here, like a different colors shows different layers. These are geological layers, like a corresponding your lithology in the area. It is like a horizontally and vertically is infinitively long. So those are like horizontal lines, like layers, sorry, horizontal layers. Here you can see this uh, the main menu of our software, EarthImager 1D. You have a like a, on the top all menu, file, edit, setting, immersion, view, tools, and language. You can change language for your own language in like your Spanish, English, or anything. You can also do it your own language. We can help you on that to change it to language. Now, all our software, like as I said, is there's a menu on the top. On the middle, in the second on the line here, you can see those here like a read to raw data, and then default is the STG file. There are 3 different formats. I'll show you briefly that. And then second is the here open inversion setting. So you can just read your data, check your setting, use default setting, which is uh, helps a lot for the getting good results. And then third here is the start inversion here. You start inversion and you can stop inversion. Once you start inversion, default setting comes for like a multi-layer measurements. I mean, multi-layer the inversions. So then if you can combine those multi-layer, which is the combining tool over here, threshold can be changed, like a default comes like a 10% default setting. And then you combine and you reduce the all these layer number until you reach your goal for expected your results. Then you can print on your screen, you can save your result, you can copy the image on the screen on the clipboard and use it in different where and your final report, for example. And here's the trial version directories, which is every time you start inverting your data, it creates subfolder of the trial directories that it will save anything you change, it will save subfolders. So the main data will never change. So anything you change, you remove your data, you edit your data, you reduce the number of the layers, and then it will all save under the trial version. The other one is here that you can show the information of the details of data, locations, and or you can just highlight the other thing. I will go through these in the software as well easily. By the way, these are like you can download these in from the handout. I already put this handout as a PDF file. You can have this webinar as a PDF, and also we will later on follow up with another email giving you the link that you can also see that video here, what this webinar video, you can go through again, or you can ask anything later on. Okay, here's like M is the generally for the distance, half of electrospacing distance, current electrospacing can be meter or feet. You can use like a meter or feet. And apparent resistivity will be generally for the ohm meters. It will not change that one. Here immersion iteration numbers, and also here if you do modeling you can put it at random noise. Okay, how let's say let's just erase all the drawing here. Yes, how you can read your data here. Okay, the first thing, so you need to enter your data manually, or you can read your data if you have a digital data, which is mainly most of the instrument has a output file. Our instrument, for example, has a STG format, and most of the instrument gives this DAT format under their data. And if you have any of these, and you can just go through read your data. But if you don't have it, you can also create like a digital data like this, like what we call the universal restricted file format, and which is easy here, shows like headers here on the first 3 lines header, and then you got here the geometry, what electrode you use on the vertical sounding, and then it will be geometry. On the bottom of geometry will be measured values, which is which electrode, current electrodes A and B, voltage electrode M and N, where's the electrode numbers here, and then voltage divided by current values. So you can prepare this easily in Excel, for example. Just save it as a URF extension, and you can just read it. If you don't have any these, just like if you don't want to prepare it, you can just go and input your data manually as well. Okay, you just go on a file, input raw data. Let me clean again here. You can choose here array type. Okay, here array type, for example, Schellenberger, Werner, which is mostly used, both 2 of them. If you like to do different things like a dipole, pole, pole, also you can do that. But these are not easy to follow up in the field, because Werner Schellenberger is widely used because it's easy to do in the field. These are symmetrical array, and Schellenberger, for example, with 3 people can handle all these movement of the electrodes and measurement. The Werner, maybe you need 4 or 5 people to do that. But when you're dipole, it's more complicated, and you need to go forward, backward. It's more difficult. That's why mostly it's done Schellenberger, vertical sounding, or Werner. So typically Schellenberger is here. What you have is here um, for each measurement, and half of current electrode spacing, and then half of voltage electrode spacing, voltage divided by current values or apparent resistive values. So you just type it these values over here on your field data, and then once you have it, you can just save your data from here. So you can easily input your data if you don't have anything to, let's say, digitally save it. Okay, one thing is in not only for this EarthImager 1D, but it's also all other software we will see for maybe if you join me later on next week. EarthImager 2D, 3D, and also the same what we create here, like a 3 easy steps, what we call it here. Okay, so these 3 easy steps, what you can do, like read your data, change your inversion setting, and then start inversion. So you don't worry about much and just choose default setting. It will save more than 90% of your troubles, and then just invert it. Once you do it, and then you can change it, your let's say from here, number of the layers, modify, combine layers, and then run again inversion. Repeat these steps until you get the good result, and then just save it and then print out your results. That's like a basic steps. So I will do this in software. Okay, and then result will be again here. Typically now you have a blue dots, which is the field data, shape theoretical data, and the red dots will be field data, and dashed line is which is following, matching each other very well. With that means is field data and then theoretical data. When it is matched, it has a good RMS. Here is RMS about 1%, but um, Generally, I recommend is RMS. If it is less than 10%, you're in good shape because it's the most of the measurement, and we have in the field errors, geological errors, some other errors we cannot control, and then we combine all these, and typically about depending on area, up to 10% can be changed. So that means is as long as your RMS error is less than 10%, you're in good shape, and you can decide. And then this is like typically a 3-layer curve. It shows 3 layers here. First layer about 200, 190 ohm meters and 30 meters depth. Second layer is about 1,116 ohm meters and 80 meters depth. And then last layer is 103 ohm meters. And this shouldn't be here actually, sorry. And because last layer depth we don't know. So in order to find the last layer depth, we need another layer here. So how do you know this shape of the curve here? As generally for like going like this, asymptotically, changing the curve direction. So you're like from first layer going to second layer. And then this curve, your field measurement is changing again. That means you're getting in the third layer. So yes, let's assume then in the field you just go another up. That means you're getting fourth layer. Like this is how the number of the layer you can decide. So this can be like done starting with multiple lines, multiple layers, and then you judge yourself and okay, this is my curve, shows only 3 layers. I end up 3 layers mainly. You can do that. Okay, before I go through over here, let's go through a software. Okay, let's go through the software. Here is the software, as you can see, is okay. Just go here, clear, erase. Okay, here I just go on file. You can see here, read data. Okay, just read data. For example, I have here is the under demo directory, one Schlumberger data. Okay, I just choose Schlumberger data. Let me show that too. Okay, just open. Okay, what you have here, black dots is the field data. Okay, this is for how the curve will continue. You can just go and edit your data here under edit menu, edit data. And then here you can see your data for AB over 2 values, MN over 2 values, voltage, apparent resistivities. So if you, let's assume you have here minus, let's say, apparent resistivity, which is my negative apparent cannot be acceptable. And you can just go and delete this number 13, for example, here. You can just delete it. You can modify it. And then if you have a duplicated, it will be get average. But if you have like a negative positive, then you need to remove the negative values over here. So that means you have here 15 data points, okay, starting AB over to 2 up to 500. And then this is apparent resistivity, and MN over to change from starting 0.5 to 8 meters, and 15 number of the data you have. So you can edit your data if you want to do that here, and then update your data here. Okay, this is like typically when I read the data, okay, and then you can see that means is the STG file format, okay, and if you want to have a DAT, you can change it to DAT. I'm not sure you see that my other pop-up window. Let me make sure that you will see. Okay, yeah, here you go. So you can see over here STG, DAT, and universal data format, 3D. Depending on your data file format, you can choose it from here. Okay, and then just open it. Again, if you don't have it, this data set as a digital format, you just go on under File and Input Raw Data. Just input your data. Just type anything starting, like for example 20 or 2, whatever is your resistivity values or voltage value, whatever you have available, you can just put it over there, and then you can do that. Okay. So it's available. Input your data, because in the 1D data you don't have it much than like compared to 2D data. In 2D data, you may have over maybe more than 300, 5,000, depending on the number of electrode and array type. You may have lots of data point. It's not possible to enter every data point by hand. So, but in 1D it is possible to, because in typically is in 1D electrical sounding, you may have 12 to 20 data points generally, and then it's easy to just type in all these measured values. Okay, once I read that, or I read my data, or I input my data, okay, what is the next step? Just default setting. Here's the in EarthImager 1D, we have just one default setting, which is comes typically, let's say, starting model, depending on the number of the electrodes. Like you have 15 data point, it will come 12 layer model, okay? And so you can here, if you know the number of the, let's say, layer here, you have typically, let's say what we said, 3 layers, right? You can just go and change over here 3 layers, okay? 3 layers. Or you can just go on default setting and just leave it as it is, okay? And then you can just start like what I said, just go on default setting, start inversion. Okay, let's just do that. Default setting, and then start inversion. So it looks like when I read that, and it will fine. But when I do for inversion, I'm getting the initial file problems here. So I have to check this my computer. Okay, just go setting here, starting model, and then here's the threshold. You can change it like a 10% or less. And then here you can just go on, if depending on the layer type, you can just type the depth, which is corresponding here thickness. You can change your thickness if you like, okay? And then if you can change all the resistivity values. Let's say if you have resistivity data information from knowing, which is from typically borehole data, and you can just put these values. You just look over here, that what that means is here, fixing your thickness and resistivity of the first layer. And then you're forcing your software to fit your data, invert your data for fixed first layer values. So if you don't have any information private, don't fix nothing over here. Just unlock all these fixing parameters. Once you have this, and then you can just go through. It will give me again an error, but it's now is okay. It's, so after first, and it's giving that. Other thing is here also, you can change your, for example, is the model over here, just like left mouse button with these blue lines, which is corresponding your the layer depth over here. This is the layer depth, for example, and then resistivity value of this layer. And then you can just change it like this, and then just go and invert it like this. So so again, here is the, depending on the values, you can play with this. I mean the through over here, or you just go starting model. You can change it from here. Okay. So typically it will work like that. Okay. Yeah. Again, I see the same thing. Starting model like this. So once you approach, and you can do that. Okay. the playing with this, and your decision, final decision will be depending on your expectation, depending on your results, and all these are related with these RMS values. Here you can see the RMS is 2.6, so this model is okay. If I change this model, for example, is for a 4-layered model, and then let me just go to another one, 3-layer model. So still is, I have RMS is 2.8, so I still get this model. So that means it's many different models, results can be, gives the same RMS value. So that means this is the typical energy of physical method, like a uniqueness of this non-uniqueness problem. The infinity solution of this, the inversion results you will get. But you need to decide which is most suitable result for you in that case. Okay, once you have it, you can just save it. You can save it this trial, and then you can use the information. Here's the on the right corner. You can just change here, just clicking or type it down, all these values over here. The measured data and the graphic title, you can change it, all this information. You can type all this also in your own language, and you can save it. Sorry about this, the problem, I have to check that. Okay, this is the more or less I have the about this EarthImager 1D. It's easy, 3-step, just read, change default setting and inversion. You can also get from technical support from us, from main office, or from us anytime you want. And here's the typical hours, working hours, and you can catch us in during working hours online as well. I just added some information about this, our products. You may know it, but you can just seeing it with different product types and software and electrodes. Okay. Well, thank you so much for your attention. Sorry about this, the trouble of the initial file problem, and I have to reinstall my software to solve that problem. Hopefully next week we will not have that problem. So I will now go through the questions. And then here I see, let me see some questions over. If you like to speak up, and you can just raise your hand, you can ask, and then we can check it. But let me just go through the questions here. Where is the questions? Okay, Victor is asking, when was the processing vertically sound data? I noticed that generally you will get a smaller error when you use 12-layer model. I have found this too tricky because the temptation is always have to use 12-layer model. Will you perhaps have any pointer or suggestion how one can know how many layers to use? Okay, I just mentioned that, but I will just go back here. Hold on. Like again, it's 12 layers. Typically, is the type of the curves in 1D, like what we call it A type, K type, and H type, and Q type. These are like depending on the going from low resistive to high resistive, or high resistive to low resistive, is changing. But you can always follow your curve, your points. Like here, asymptotic values goes from like a horizontal almost, and just going up now is your measurement. That means you're going from one layer, one zone to another zone. So that means this part shows like a 2 layers. Yeah, now I continue our measurement, and then I'm going to turn again this curve turning down. That means we're getting in the third layer, third zone. So that's like how you continue. Any change you see on your curve, but these are like smooth changes, not sharp changes. Sharp changes means general for noise or some other things during the field measurement. So sharp changes cannot be considered another layer generally. But some smooth changes, yes, always you consider as a
small, as another layer. Okay, Victor is asking, is the second question, when acquiring data using Venner array for smaller spacing, for example, 25 centimeter, we sometimes struggle to get reading. Would you know what is the cause of this and what one can do about this? Okay, the second, he has 4 questions, but okay. Uh, okay, if you have a very small distances, and Victor has our super string array instrument he's doing. Um, if you have sometimes what happen if you're too close, and then if you're giving, let's say, uh, uh, especially for current electrodes, sometimes close to potential electrodes, or your current is injecting lots of voltages at that point, you have a good contact resistance, you're just injecting lots of like a 400 volt almost, but you have a very small spacing and voltage saturation can happen. So that will give you some error. In that case, you can repeat that, or the general our instrument design to repeat automatically reduce that high voltages and then try to get the optimum data. So that means this is typically you will see on our instrument like input overloaded error. And then, but the instrument will repeat that and then change your automatic gaining and also the dropping down the voltage and then eliminate the saturation problem, and then you read that good data. If you have a, if you repeat that still is doing it, you can just go on man uh, the setting of the current and voltage setting. You'll lower down your current or voltages and you will get this generally is a 10 good reading. Okay, how about the third question of Victor? How necessary would you say is to do measure contact resistance when doing? Okay, this is uh, you need to do make sure that your whenever you change your current electrodes, make sure those are has a good contact. Even if vertical thick sounding, you will see that resistance values on the measurement. But I will always recommend to go to menu tree 1 to check contact resistance of that point. So that try to reduce your contact resistance is less than about 2000 ohms to get a good reading. And resistivity less than 5000 is okay, but is keep in mind it's less than 2000, less than 1800 ohms contact resistance, always you will get a good readings. Okay, the last question of Victor, when you are unhappy about measurement in the vertical and you remeasure, does a superstring have both readings separately at every step? Okay, what we remeasure, and I mean repeat the measurement, and superstring, it keeps all these measurements. So we don't remove anything, we don't replace it, we just keep it. When you read an EarthImager gets average of these readings. So sometimes you may get very noisy data. That's why like on the edit menu on the data, you want to just go edit menu, edit your each data and remove that high noisy data, maybe a negative upper resistive value, then avoid that averaging will be misleading your getting the wrong or noisy data. So try to, you can do manual or you can just edit it. Okay, Najib's asking, software can correlate between two sounding. Okay, you have the software only gives in the results of every sounding separately. So we don't have any option to putting all these in second sounding next and then make maybe hand drawing or something. So we don't have it, but you can get these results in uh, as a digital results or graphic results, and then you can just combine these in different the platform like a Grapher, for example, Surfer, or any graphic type, um, or a PowerPoint as well. You can do that. But software doesn't give, the next to each other doing and combinations. What it does is that can be done in EarthImager 2D. That means you can combine multiple vertical ethic sounding data and then make 2D inversion. That's different things. But in EarthImager 1D, you can just do one at a time for each data. Okay, one other, the Birema is asking what does RMS stand for? RMS is root mean square, is like a estimated average generally between differences between measured data and theoretical data. Theoretical data, what we calculated from this program here is giving electrical model, geoelectrical model, and corresponding this dot line, for example. So that will let me just go to next one here. Here is based on the three-layer model. We have this red points and blue points. So one is the theoretical model, theoretical data, which is based on this model. Another is the field data. So differences between this, what we call root mean square, about here 1% more or less. So again, consider this about less than 10%. So you don't have to go like a 1%, 2%. A good data set generally for just inversion, like a couple iteration, like 2-3 iteration. Here you can see like 3 iterations. At the end of 3 iteration, you get a good RMS, and then you get good match actually. Then you can come back over here, for example, this icon over here, and then just go on earlier one, and then you can compare it. Okay, the another question, what software do you recommend for borehole siting? 1D, 2D, or 3D? Okay, borehole siting is okay. You can have any 1D, 2D, 3D data in the wherever your borehole is located. But this is typically maybe a question for groundwater investigations for borehole. You have one borehole, you have like a you don't have a 2D data, then you can do just do 1D. And in that case, and try to do is 1D close the borehole. But don't do exactly what the borehole is, because sometimes the borehole is a metallic casing, so that will give you some noise on your measurement. Try to apart a little bit on the borehole to do that. Try to get your data there. So the borehole information will be the good information you will obtain for starting model of your inversion. Try to obtain the good result and compare with the borehole outcomes with that one. But if you have a 2D data in the area, that will be much easier to interpret that generally with borehole information, because sometimes 1D data, I mean the general, not sometimes, but always, 1D data gives you just vertically is a changing of resistivity. It doesn't give any lateral changes. So sometimes in the borehole area, you have a fracture. In the 1D, you cannot find it. So in that case, you need to go to 2D to do that. Okay, Muhammad is asking is which method EarthImager use for inversion and then forward. Uh, this is the 1D inversion is the rich regression method we will use for the 1D inversion. Okay, Dr. Alarbi asking, if you don't have any prior information, how can we determine the initial model for EarthImager 1D? So some software really rely on inflection points of measurement, sound, data curve, and okay. If you don't have any initial model, again, what I said is just go to the read your data, start default setting. Default setting will give you multiple layer. So start with that one always. Start with that one. Just go invert it and then combine, later on combine to the layers. If it is like it's changing more than 10% between the layer, like resistivity values or in the area, then it will combine. But if you know the shape of the curve, which is like here, we know this is a 3-layer curve, and I end up 3-layer. So then I can give 3 starting model like just starting like this. So I can put this initial parameters. Here is do you see the first measurement is about 100, which is here 200 ohm meters. Okay, upper resistive values. Here I can see 1, 2, 3, 4, 5. First 6 measurements about 200. So my first layer will be starting about 200 here, like which is I get like a 200, and then I am going up. So asymptotically, I extend this to this this line over here. Let me just draw like a line over here. Okay, asymptotically I am just going to like this, okay, and then you just go through like this asymptotically. So that means is that this line over here, it will give you generally where you will go through it, and then so that means for second layer, and at least you will start second layer estimations about here 300, 400, 500, 600, about 6, 700 ohm meters. So here we end up second layer 1000. So you can start second layer apparent resistivity is 6, 700. And the last one is going down. So last one is just going, we don't know where it's end, but I mean, you can also put about less than 100 ohm meters. So which is like a, this is the estimation you can start. How about the depth estimation? So when I go through like this here, these asymptotic relations, generally what it start like from here, first asymptotic relations, either you can be like a here. In the past, what we used to have is in the master curves. We put these master curves on the top of it, and we know exactly where the depth thickness of these layers and the rest of it values is changing. So here is between 10, 20, 30 maybe, you can start first layer thickness. And then the other one is here, it goes like the same way over here, like here, maybe about this point, maybe is 100, 200, between 100, 200. So less than the first one. So it will be about maybe it's typically you can put 100 meters depth, and then you can start with this the initial model in that case. Okay, the Brahma is asking when they explain the different array type and layout further webinar. Okay, it's like what I said is in EarthImager 1D, you generally use Schellenberger and Wenner. So this is the typically two array you use. Mainly use Schellenberger because it's easy to handle in the field with 3 people. And then Schellenberger also gives better information and depth compared to the Wenner. So typically in the if I am doing in vertical examining, I would prefer to do always Schellenberger. But then other array type, we will see that in EarthImager 2D the next week, hopefully, uh, and other array types, and those are important there in the when you do 2D, 3D measurements. Okay, the Ali Akbar is asking, what is the effect of current temperature while doing Wenner or Schellenberger sounding? Okay, the current temperature is your the working area temperature, I think, uh, the affecting. So the outside temperature can be 40 degrees, 50 degrees. Nowadays in Spain here, we're suffering hot temperatures, almost 40 over 40 degrees. So that means this doesn't affect my measurement, but that effect is the working condition on the field. So the cable will be like almost, if you leave it in hours and hours under the sun, it's very hot. And uh, that means is all the ground is very dry, and you need to improve. You need to pour water, salty water, to improve contact resistances. In that case, especially like a dry seasons. I mean, for areas like Ali is working in the Middle East area, is some places very dry sand, especially, or sand dunes. In that case, is the is not a condition of affecting my results, but what affect is your measurement. So that means it gives high contact resistance, and then that means when you have a high contact resistance, maybe and sometimes you get a high contact resistance 30,000, 50,000 ohms. That means I cannot inject very good current over there. Maybe then I'm injecting less than 20 milliamp currents, 10 milliamp currents, 2 milliamp currents. In that case, it's very weak. So I will get, that will result me the noisy data. So that I want to avoid that. So we just launched it like last week, I think. Let me just go through there. Maybe I can show you. Is the blog post about reducing our contact distance. I will suggest you go through that our blog post, and then you can find out how to reduce your contact distance. That's the main issue in general for the data quality. So another thing is that he's saying how much electrode needs to be. I lost his another question. Okay, how much electrode needs? I think for if the question related contact distance, and again you can put many different electrodes in same location to increase this surface area of then reduce the contact distance. Okay, I got another questions here. We got many questions here. Okay, Muhammad is asking, what are advantages of each image compared with other software? Okay, here is the this we're talking about the EarthImager 1D. You can easily, change all your these graphically or manually. Your input data, your model, your inversion result, you can adjust. As an output, and you will have, let's say, uh, JPEG results that you can put easily. You can put all your the field information, like what I said, is in the on the left lower corner, and then you can save it this as a result and just put it in your the final report. So you don't have to do anything else. That will be all easy to do that. I don't know the other software which back there are many other softwares. There are I cannot say comparison with those. Okay, last question of the Birama. It seems to me that the first layer is 20 meter. Why you select 30 meters? Okay, that's my input. So initial model. So I'm putting, okay, I'm guessing about 10, 20 um, meters of the initial on this one. But my inversion result, it shows me, it says, okay, your theoretical value match is with this parameters, like a 30 meter, 80 meter, and then 200, and it match easily, I mean, much better to the other one. So what you can do generally in this kind of the cases, you just go back here to do like a 2D, second iteration, first iteration, try to find out to do that. Let me try to do, if I can do that, because I got the trouble in the early with the software. Here you can see that, let me just get rid of this pen over here. Okay. Okay, I just go through here. Here you can see I have a 5 iterations, and 5 iterations shows is RMS2. I might just go back here, iteration 4. Do you see that? Now I have iteration number 2 is RMS 16. Okay, and now 3 is okay. It's like a less than what I said is 10, less than 10%. So that means then I am a good shape. So that means this is also correct. Okay. Next one, this is also correct. This is also correct. Do you see that? This is the depth is changing. So that means is you need to decide what so depth corresponding. The thickness and the depth of the or model parameters corresponding relative. We don't know. So those are all estimated. So that means the software will give you a range for changing like a maximum minimum what can be that you can always evaluate, but this change between maybe about 10% left and right, so maybe it's just changing the between um, depth of each layer, residue of the layer is changing a little bit, not much, except if you're giving initial matter is wrong, and then you end up the wrong result generally. So, but typically initial model, as what I said, you can pick it up yourself, or you can just leave the software pick it up itself, and for multi-layer, and then you reduce it to like a 3 layer at the end, you end up at what you expect. Okay, Ali is asking again, how much electrode needs? Okay, how much electrode needs? Okay, let me understand your question is, okay. You mean is how many electrodes you need for this? For vertical sounding, you need just 4 electrodes. So A, B, current, M, and voltage. You just do manual measurement. Just go to 4 electrode manually. You change the positioning, like here, what we say AB over 2. Okay, just go back here to just AB over 2, and then just MN over 2, and just read the measurement for next point. That's for needs for electrodes. Okay, another question. I don't use very often 1D resistivity data, but instead 2D, 3D. Okay, this is Dr. Alarbi asking. Is question is that, can you improve EarthImager 1D so that if one has only apparent resistivity data and AB, MN distance, the software will be able to compute the potential data? Okay, let me understand this question. Is the okay, if one has only apparent resistivity data and ABMN distances, software will be able to compute the potential data. You mean is 1D or you mean a 2D? So that means if you're going from 1D to 2D, that yes, you can do that. You just combine 1D data to do 2D results. So you can just make this the which is the theoretical values is what you're showing here is the voltage values, which is your potential potential values. So like you mean the modeling maybe? Yes, if you can give this the uh, your measuring geometries like a positioning A and B MN, then you can calculate modeling. That means your potential. Yes, you're right. You can do that also. Okay, the Ali is correcting his question. I meant length of electrode into the ground for sounding. Yes. Okay, the generally for what we have a stainless steel electrodes about 45 centimeters, 60 centimeters. That means is depending on your electrode spacing, you can put all the way down like 30, 40 centimeters. So that means if you're using maybe 1 meter electrode spacing, then you're not going to put 40 centimeters. Then you just need to put about 10, 15% of that distance, like 10, 15 centimeters, 1 meter electrode spacing. If you have a 10-meter electrode spacing, then okay, in that case, you can put 40 centimeters all the way down to electrodes. That will be create a good, better contact in the ground. Okay, that's so far I have these questions. I'm not sure if I miss any question. If it is not, well, I just finished the webinar over here. Well, thank you all for joining me today, and I hope you enjoy. We will follow up with email and then for recording about this webinar.